Hello. Um, my children are home. They're quiet for now, but if you hear screaming children, everything is okay. um, Youngman designs a concrete bird bath. The bird bath is supported by a pedestal. This is shown in the diagram. Okay. The interior of the bird bath is in the shape of a cone with radius r, height h, and a constant slant height. Okay, so this is the slant height of 50 centimeters. Write down an equation in R and H that shows this information. So we are writing down an equation in R and H that shows this information. Okay, so we know that if the height is here, the radius is here, and there's a constant slant height of 50 centimeters, and this is a right angle, we know that the relationship between all three of these things is going to be the Pythagorean theorem. So we would just write r very thick. R squared plus h squared is equal to 50 squared. So 6b says let V be the volume of the bird bath. Show that V is equal to 2500 pi h divided by 3 minus pi h cubed divided by 3. Okay, so the volume of a right cone, that's the figure of this top of the bird bath here. That formula is in your formula booklet, okay? And it's given as follows. So the volume of a right cone is going to be 1/3 pi r squared times the height. Okay, so if you'll notice, R and H are familiar items. They are up here. Let's pick one variable in order to be able to use it further on in the problem. It looks like they have V in terms of only H. Okay, so we are going to want to solve for R in terms of H because there are no R's in here. No R's, only H's. Okay, so we have R squared plus H squared is equal to 50 squared. We're going to want to get R squared is equal to 2500 minus H squared. R is equal to the square root of 2500 minus H squared. Okay, perfect. So now we have it in terms of H's only. So we're going to substitute that into our volume of a right cone formula. We have volume is equal to 1/3 pi times the square root of 2500 minus H squared. All of that is squared times an H. Sorry. We then have the volume is equal to 1/3 pi. And then there's an H out front here. And inside we've got 2500 minus H squared. So we're going to go ahead and distribute the pi and the H and the 1/3 to each piece in the parentheses. And we would get volume is equal to 2500 pi H divided by 3 minus pi H cubed divided by 3. And that perfectly matches the volume given above. So we'll give it a little check. A little checkerino. Okay. Yeah. Now 6c says to find dVdh. dVdh. So that's the derivative of the volume with respect to the height. So we have dVdh is equal to, and we're just going to go ahead and take the derivative of this guy right here. Okay. So in order to do that, remember that 2500 pi divided by 3 is just a constant. H is the variable that we are going to disappear, and we would be left with 2500 pi divided by 3 minus, And then remember that pi is a constant here, so we would get 3 pi times h squared divided by 3. These are going to cancel. And we would get 2,500 pi divided by 3 minus pi h squared. So that is dv dh. All right. Let's go to 6D. So 6D says, Hyungming wants the bird bath to have the maximum volume. Okay, now we are getting into some optimization. Awesome. Maximum volume. So our optimizer is going to be the volume of the right cone, and it's going to be a maximum. Cool. So using your answer to part C, find the value of H for which V is a maximum. So we know that when we set the derivative equal to 0, we're going to find the locations of possible maxes and mins. So let's take the derivative that we found right up top here. Okay, so it's going to be 2,500 pi divided by 3 minus pi h squared. And we're going to set it equal to 0. Excuse me. So this was a no calculator question, so we're going to have to go ahead and be careful with our math here. Okay, I moved the pi h squared over, and then now I'm just going to cross multiply so I can solve it. 3 pi h squared is equal to 2,500 pi. I'm going to divide both sides by 3 pi. Sorry, that is my son. And now we have h squared is equal to 2,500 over 3. We're going to square root both sides, and we'll get h is equal to the square root of 2,500 over 3. Sorry, that's a little misleading. Let me just make it more clear that we're taking the square root of everything. There we go. So now I can know that the square root of 2,500 is 50. The square root of 3 is gross, so I'm going to leave this in an unrationalized version right here because I know I'm going to be squaring stuff as I get further on down in the problem because it's going to be asking me to, plug this into other stuff. So I'm just going to leave it like this for now. Oh, I do need to confirm that this is in fact a maximum. Let's go ahead and test this on the number line, okay? So I've got 50 divided by the square root of 3. This is when the derivative is equal to 0. I'm going to go ahead and test the derivative for a number below 50 divided by the square root of 3, which is it's like around 28-ish. It's between 28 and 29. So it's like let's say 28.9. Okay. So something below that, let's test it in the derivative. That's going to be a positive. I'm going to test this in the derivative. Let's test like 30. Okay, it's going to be a negative. All right, so in the original graph, if I'm going from increasing to decreasing, that in fact confirms that we have a maximum volume when the height is 50 over the square root of 3. Okay. 6E, find the maximum volume of the bird bath. Well, we have a function for we have an equation for volume as a function of height, and that's going to be taken from above. It's 2,500 pi h divided by 3 minus pi h cubed divided by 3. So now we're going to substitute in that height that we found up here, the height where the volume is the maximum. And that was at 50 divided by the square root of 3. This is why I left this in unrationalized form, because I knew I was going to be like cubing it and stuff. So I'm like, okay, I'm just going to leave it as a radical for now, and we'll see where we get. So we have 2,500 pi, and then I'm subbing in that value for h. This is all over 3 minus pi 50 over the square root of 3 cubed divided by 3. Excuse me. Oh, wait, this is not a calculator question because you can definitely have to type that in your calculator to solve. But it does make it a little easier with the square root. Okay, let me do this off to the side. You've got 50,383.3156. What was it? Centimeters? What were the units here? Centimeters. All right, so we've got rounding. (50,400 cubic centimeters) is going to be the maximum volume of the bird bath. So 6F says to prevent leaks, a sealant is applied to the interior surface of the bird bath. Find the surface area to be covered by the sealant given that the bird bath has maximum volume. Okay, so we need the surface area of the cone. And that is in your formula booklet. Okay, so we don't need the bottom. We don't need this part here. We just need the walls, right? It's like if we were just like painting this piece in here. Okay. Just these walls in here. We just need to paint those walls with the sealant. Okay. So we just need the surface area of the interior part of the cone. Okay. And that is in our formula booklet. Excuse me. Under cone curve. Okay, so go ahead and pause the video, find it in the formula booklet, and come back in a second. Okay, hey, welcome back. You should have gotten that the surface area of the cone curve is equal to pi times r times the slant height L. So we have the surface area is equal to pi times the square root of 2,500 minus, this was for r. Where is r? There we go, up here, 2,500 minus h squared. Okay, great, we can totally do that. Minus 50 divided by the square root of 3 squared. This is why we left it in square root form, yes. And then I made this way too long. Times the slant height, which was given in the beginning of the problem as 50. So now we have the surface area is equal to 50 pi times the square root of 2,500 minus 2,500 divided by 3. And now we have a surface area that is equal to 6,410 square centimeters, since we're talking about surface area. The end.